Welcome back, physics fans, and here we're going to do quiz 76 from the Masteries. A 2,400 kilogram space boulder is dropped from a height of 7,500 kilometers above the surface of the Earth. What is its initial potential energy of the space boulder? And that's relative to zero being at infinity. Then the second part of that question is, what is its final potential energy? What is the change in potential energy? And what is its landing speed? 4 parts to this question, and there's actually a hidden fifth part. Okay, so it's initially starting up at 7,500 kilometers above the surface of the Earth, but we have to go and measure it from the radius of the Earth. What did we have? Well, we have a hint here. Relative to zero at infinity talks about that we could calculate the potential energy of the object to being Gmm over R, and it's negative, and it's with respect to being at infinity. So we have infinity way out here. Let's just put infinity way out here, and we have a distance out here, and that's the potential energy loss from infinity to here will be a negative Gmm over R. So we calculate the potential energy initial, which will be negative Gmm over R. That's going to be 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th. And the mass of the object is 2,400 in kilograms. And the R here is the separation distance between these two objects, not infinity. Even though we're measuring it with respect to infinity, the R is the separation distance, so the center of the Earth to the height there. So we have to add the radius and the height together. So this will be 6.38 times 10 to the 6th, that's the radius of the Earth, plus 7,500,000 meters. Okay, it has to be in meters. So we will go G m, mass of the Earth. I already have these numbers programmed in as constants, times 2,400, divided by bracket, the radius of the Earth, have that in there as a constant too. And then I have to add 7,500,000. And I get a value here, and it's negative because the formula says it's negative. And it's 6.897 times 10 to the 10th joules. Okay, it's negative because it's zero at infinity, and as it falls, it loses potential energy. And how much does it lose? About 69 billion joules. Okay, now the potential energy final, when it lands on Earth, is given the same formula. Okay, but kind of clash together. I don't even want to fix that, I don't think. Let's see if I put a dot down if it'll fix it. Nope. Let's copy it again. See if I can cheat one more time. That works better. But this time, we don't include that height because it's on the surface of the Earth. So we don't have to do it above. It's the same constants above, the mass of the Earth, mass of this rock. So I'll just take this previous done number and go over here. And that'll be the energy on the surface with respect to infinity, negative 10. negative 1.5, sorry, 00 times 10 to the 11th joules. This is my infinity mark. We have to calculate the change in potential energy. And if we look on the Moodle, on the question itself, it even reminds you the answer is negative because we're going closer to the Earth. As we lower down towards the Earth, it's going to lose potential energy. So it better be, the change better be negative as it goes down towards just how potential energy is defined here. So we take the final, subtract the initial. They're supposed to be both negatives. So take the final, subtract the initial, and I get a negative 8.108 times 10 to the 10th joules. That's how much energy it loses going from 7,500 kilometers above the Earth to the Earth. So that's how much energy is lost. That's how much kinetic energy is gained. Because the loss of potential energy will be the gain in kinetic energy. So gain in kinetic energy will be the positive number of this. Okay, and since kinetic energy is 1/2 mv squared, we have that kinetic energy. We can calculate for velocity now. Velocity is going to be the square root of 2 times the kinetic energy divided by the mass. I'll write that down. 2 kinetic energies divided by the mass of the object that's moving. So I'll take the square root of 2 times that kinetic energy divided by the mass. The mass is 2,400. So I get a nice, good landing speed of 8,220 meters per second. Okay, zoom out a bit so I could do my second part of this question. So this was my answer to A, and that's B, that'd be C, D. Now, the second part is physics done wrong. What happens if we dropped it and we just considered using potential energy as mgh? Okay, assuming that g was constant as it fell towards the Earth. It's wrong. So we'll get a value that's wrong. But let's see what we get. So mgh is going to be going to the 1/2 mv squared of its landing. Cancel out the m's. And we get v is equal to the square root of 2gh. So the square root of 2 times 9.8 times 7,500,000. Yep. So it says a landing speed of 12,124 meters per second. Okay, that is wrong, but it is going to be faster because it thinks that it's a constant gravitational pull, but we know that gravity is less out here, so it'll be less of a pull to the same pull, mgh. So yeah, we expect a little bit higher. Anyways, welcome back, and thanks for listening to this. And now you click on it, subscribe, leave me lots of comments, and don't forget to turn on the notification bell. Thank you very much. Bye now.